Hi, I'm Andrés Rabuñal, and I have just started my second year working under the supervision of Jaume Navarro Caballé and Pablo Fajardo Peña in the experimental characterization of electrodeless plasma thrusters for very low Earth orbit applications. So, the main particularity of my thesis is that it falls under the concept of air-breathing electric propulsion that differentiates itself from conventional electric propulsion because instead of using noble gases as propellant, the concept is to reduce the altitude of the orbit to very low Earth orbit to between 100 and 300 kilometers so that the air density is high enough that you can put an intake in the front of your spacecraft and gather the atmospheric remnants that you can find and compensate for the drag by ionizing it. My thesis focuses just on the thruster part, and among the different technologies that have been proposed for that, I use helicon plasma thrusters that, when compared with other technologies like the Hall thruster, have the advantage that it doesn't have any cathode of neutralizer, so you don't have that problem of atomic oxygen erosion, and that they are typically operated at lower power. But on the other hand, they are a much less mature technology, and they have very poor performances, basically. My thesis is divided into four main phases. I started with a characterization of one of the devices that we have operating with air to find key behaviors and key operational points. And later, we will try to understand these key behaviors by analyzing plasma discharges under these conditions in order to extract information to be able to modify the prototype to optimize it to use it with air, and then characterize it again to see if the modifications actually worked or not. So the device I'm using right now is the HPT-05M, developed jointly between Sener Aeroespacial and UC3M, that basically has an antenna that excites helicon waves and TG waves in the tube with the propellant, and with a solenoid you generate a magnetic nozzle and you create the plume. And the experimental results I'm going to present today is a parametric analysis of the variation of the power, the magnetic nozzle intensity at its peak, and the mass flow rate. So the diagnostics that I used in this campaign are a Faraday cap to measure the ion current, a retarding potential analyzer to measure the ion energy, although I'm not going to present the results here due to time constraints. And the main novelty of this work is that we also use a thrust balance that represents the first time that there have been direct thrust measurements of an HPT operating with air. There have been indirect thrust measurements and direct thrust measurements with oxygen or nitrogen, but not with air. And this is critical because of the huge complexity of plasma chemistry operating with air. To just give a small idea of this complexity, you have that plot that represents the different reaction rates for different electron temperatures that we can find. And the main takeaway is that the dissociations of your species are much more probable than the ionization. So it is expected that before ionizing your plasma, you are going to dissociate your molecules, and therefore your average mass is going to be lower. And this has a huge impact because the propellant utilization efficiency directly depends in that average mass. So we took the most conservative approach possible, and we assumed full dissociation. So we are divided our efficiency estimation by 2. So going into the results, we can first start analyzing the total current on the beam. And the first thing that we can see is that if you increase the radio frequency power, your current increases as expected. And the first important finding that we can have in this campaign is that for all powers, there are 2 clear regions with respect to the mass flow. One below 13.5 SCCMs, where your current increases when you increase the mass flow, but then it saturates at different rates for every power, but it always saturates. And this is important for the air breathing. And the effect of the magnetic field is not really clear yet because the campaign is still going. Some of these measurements were taken yesterday in the evening after the doctoral meetings, so I didn't have much time to go through them. So the magnetic field is still a problem, sorry. And it is still more a problem when we look at the propellant utilization efficiency. First of all, we can see that the value is pretty low with a maximum of 16%, but take into account that this is in the most conservative approach possible. If we consider null dissociation, this would be a 32, that is not that bad, but let's be conservative. And with respect to the power, we see the same tendency. It increases when you increase the power, and the magnetic field is still less clear in this case because for high values of mass flow, it doesn't seem to have an effect. But this is really strange behavior at the low mass flows that is repeated for all the different powers. So it's either a systematic error in the experiments or it's some behavior that is there. But as for the moment, I'm almost clueless about this. And I say almost because if we look at the thrust in this view about the constant mass flows, we can have some insights into it. But first, well, the thrust is always lower than 1 millinewton, which is pretty low even for EP standards, but it was expected due to the low mass of the air. And with respect to the radio frequency power and the mass flow, we can extract the same conclusions as before. Radio frequency power increases the thrust, and it also saturates. There is no difference basically between 13.5 and 22.5. But the main finding of this is that for each mass flow and each power, there's always one specific value of magnetic field that maximizes your thrust. And if you increase the radio frequency power, this goes to higher values. It will do like this. You can clearly see it. But if you increase your mass flow, it goes to lower values. So instead of being here, passes to here, and then passes to here, from 1200 to 900 to 600. And this is considered crucial for air breathing because we can imagine a situation when you are in orbit, like operating here, fully doing the thrust you need to compensate for your drag, but suddenly the air density increases maybe because of the solar activity, and you pass to here, and you have two negative effects. The increase in drag because of the increase in the air density, but you are in the detrimental region, so you lose thrust by increasing your mass flow. So you could either increase your radio frequency power to compensate, or if you have the capability, reduce your magnetic field to follow this line and increase your thrust by reducing the magnetic nozzle. It's very counterintuitive. It is not yet very well understood, but to try to understand it better, I was working in a B-dot probe that basically is a loop that we can use to measure the helicon wave and how it propagates during the plume, and how is the power coupling for different thrust configurations. This works basically due to the Faraday induction law, and with one calibration parameter and using an oscilloscope, we can reconstruct the shape and intensity of the helicon wave in the plasma. So I designed a 3-axis B-dot probe that you can see here, and it is composed of 3 loops, concentric, really small. The biggest one has a 2.7 millimeters radius in order to keep a constant field inside it. And in order to have some signal integrity improvements, I applied 3 different methods. That is using an aluminum foil as electric shielding, a center tap transformer to filter the capacitive pickup in the twisted pair that goes through between the loop and the electronics, and putting the electronics inside a Faraday cage. And in order to improve the signal-to-noise ratio, I put for each axis a dedicated L-type matching network tuned at 13.56 megahertz. And in the end, I achieved around minus 20 dBs for each axis. That means lower than 10% signal reflection. I should have taken a photo of the real PCB, but I sealed the Faraday cage before taking the photo, and I didn't want to open it because I would have to calibrate again. And I don't want to do that because the calibration is a nightmare. It is much more complex than we expected at the beginning because of the non-trivial interaction between your calibration setup and your probe. I designed a Helmholtz coil. This simulation is to make sure that inside the volume of the probe, the magnetic field is constant. And this is the setup of the calibration with a network analyzer. The port 1 is connected to the Helmholtz coil through a dedicated matching network. It's not fancy, but this has a purpose. And the port 2 connected to your B-dot probe. And when using a network analyzer for this, you have basically 3 important parameters. The S11 that measures the reflection on the port 1, the S22 that is basically the same for the port 2, and the S21 that tells you how well these two are coupled. What you transmit in the port 1 and how it's received in the port 2. And we found that this non-trivial interaction is very important because if you tune your Helmholtz coil, here the higher the value, the better the transmission of the Helmholtz coil, your sensitivity changes a lot. Think about it carefully. You don't need to be a genius to imagine that in order to calibrate what essentially is a receiving antenna, you would have a good radiating antenna. But it took me more time than I want to admit to realize that. So it was a really long process. And this has to be tuned manually, modifying this matching network to find this curve. But it saturates, so we are confident that this is the actual value. And in the end, we found that the sensitivity of this probe is approximately 1 order of magnitude higher than the state of the art because of this dedicated matching that we did for 13.56 megahertz. For the rest of the frequency is state of the art. And the conclusions would be that this was the first air breathing test of our institution and the first direct thrust measurements with air with helical plasma thrusters that are in the literature. That it might be necessary to include in your satellite ability to modify in orbit your magnetic nozzle because you have more range of maneuverability to modify your thrust. And the calibration of a VDOT probe is a really complex process that really requires to take a lot of care in the setup. And the next steps will be to perform the VDOT measurements in this month, hopefully, to develop a 0D global model for the composition of the plume that I already started it, but it needs some refinements. To use optical emission spectroscopy and the corresponding collisional radiative model that I already did the literature review for that. To develop a drag versus altitude model to try to assess the feasibility of using this thruster for air breathing. I already did a small model for that, but it also needs some tuning and to characterize better the hypothesis, and in the long term to optimize the thruster to be used with air. And as Mateo said, I was the captain of the football sala team in the department, so another milestone. And this is all.